Hello everybody, this is your last video in this Unit 5 on probability. This video is all about the geometric distribution, the geometric probability distribution. So this one is a little bit less common than the binomial distribution, but it does still show up fairly often. So I want to make sure that I made a video about it and talk to you about what this distribution is. Geometric probabilities are a little bit easier to calculate than binomial probabilities. There's a little bit less going on in the formula, okay? But just like the binomial formulas, you have access to all of the geometric formulas on the formula sheet. So these are not things that you have to memorize, okay? So just to remind you, a binomial setting or a binomial random variable, the goal is that you have a fixed number of trials and you're trying to count how many successes you get within those fixed number of trials. A geometric setting is a little bit different, okay? A geometric setting, or in a geometric setting, the goal is to repeat a chance behavior. So drawing a card from a deck of cards, flipping a coin, rolling a die, etc., okay, until a success occurs, okay? So what you record, right, you record the number of trials it takes to get one success with the probability staying constant each time, okay? So if you were, for example, rolling a dice, right, and say the goal was to roll a 3, you would keep rolling and rolling and rolling and rolling the dice until you got your first 3. And once you got your first 3, you would stop, okay? So what you see on the bottom of the slides on the left-hand side is your formula for geometric probability, and you're trying to find success on the kth try, okay? So you're finding the probability that I used y for the random variable, but you could use x as well. I just use y because that's what they use in your textbook. So you're finding the probability that y equals k, meaning that you get your success on that try, that kth try, okay? So that equals the probability of failure, so 1 minus p, so that's the probability of failure, to the k minus 1, right? And then multiply that by p, right? So this first bit, the 1 minus p to the k minus 1, is all of your failures, right? So let's say you're rolling a dice and the goal is to roll a 3, right? And you want to figure out what's the probability that you don't roll a 3 until the 5th roll, right? So you have your failure probability, and you're going to get that failure probability 4 times, right? 5 minus 1, because the 5th time you're going to succeed, right? You're going to roll the number that you were looking for, the 3, okay? So in this type, with this type of variable, k is not the number of successes, but rather when the success occurs. Right, so i.e. on the 4th trial, right? So that would be k equals 4 means success on the 4th trial, okay? And then p is still probability of success, okay? And there's one thing that I did not mention with the binomial variables that I probably should have, which is this, okay? Every once in a while, you'll come across a problem and they will ask you to find what's the probability that at least one of these things is true, okay? So whenever you see that phrase, okay, if you're thinking about at least one, that means that this value of k right here could be 1, it could be 2, 3, 4, 5, right? And that could go on and on and on and on forever, right? So rather than having to calculate that the long way, the way that we find the probability of at least one, insert thing here, is 1 minus the probability of none, okay? Right? Or the probability that y equals 0, or in a binomial distribution that x equals 0, right? So that formula works in basically any probability distribution, but it comes up the most often in geometric distributions, okay? Just like binomial distributions, there's a calculator path that you can follow. So you just go to a regular calculator page on your TI Inspire. Your path is you click the menu button, and then you choose the statistics menu. Then you choose the distributions menu. Okay, and then you choose either geometric PDF. So that would be like for a y equals k, or you choose geometric CDF. So that would be like y is greater than k, or y is less than k. Let me draw my little arrows in here. Okay, so that is your calculator path, right? Okay, for binomial distributions, you have a formula for mean and standard deviation. There's not really a formula for standard deviation for geometric, but there is a formula for the mean. Okay, the way that you calculate the mean or expected value of a geometric distribution is you do 1 divided by p, which is the probability of success. All right? Okay, so let's take a look at these last couple of problems here. Okay, so I'm telling you that in these problems, the probability of picking Wolverine is 0.6, and the probability of picking Mouse is 0.131. Okay, so this first question says, what's the probability that at least one of 5 randomly selected students voted for the Wolverine? Okay, so rather than finding probability of y equals 1 plus y equals 2 plus y equals 3 plus y equals 4 plus y equals 5, ugh, that's so many, right? It's much easier to say the probability of at least one, okay, equals 1 minus the probability of none. Okay, so, and we're talking here about at least one of the students voting for Wolverine. So this probability of none is saying that none of the students voted for Wolverine, okay? So if none of the students voted for Wolverine, then that means they voted for something else. So that probability is 0.4, right? Because the probability of success is 0.6, right? But I'm saying none of them voted for Wolverine, and there were 5 randomly selected students. So I'm just going to raise that to the 5th power, right? So basically what we did here is we did 1 minus 0.6, which is 0.4, to the k minus 1. And in this case, k is 6 technically, right? Because we're saying we're getting our final success on the 6th person, right? But none of them chose the Wolverine, so 0.4 to the 5th power, right? And then when you actually calculate all of that, you get it's 1 minus 0.01024. So that final probability is 0.98976. Okay? Which makes sense, right? Because we're saying at least one, so that's going to cover almost everybody, right? So that probability is going to be large, right? Okay. The second part here says, what's the probability that at least one of 4 randomly selected students voted for the mouse? So again, we're going with probability of at least 1 equals 1 minus the probability of none. Okay, we're saying at least 1 of 4 did vote for the mouse. Okay, so here we're doing 1 minus the probability of none, meaning that none voted for the mouse. So that would be 1 minus, if the probability of voting for the mouse is 0.131, this is 1 minus 0.131. Okay, and if none of them voted for the mouse, then I'm going to raise that to the 4th power because there were 4 students. So this is 1 minus 0.869 raised to the 4th power, which is 1 minus 0.57. So your final answer is 0.43. So that is my final answer right there. And I probably should have circled this one at the top as well. Okay? All right. Then, last set of questions here. This person is writing an article. He wants to interview a student who voted for the mouse as the mascot. He's going to randomly select students until he finds one who voted for the mouse. Okay, so we're trying to find the probability that he doesn't find someone until the 5th person. So that means K equals 5, and the probability of success, because we're talking about the mouse, is 0.131. So I'm going to plug this into my formula for the geometric distribution. So I'm finding the probability that y is equal to 5, right? So what that is, this, right, y equals 5 in just in plain English is we're finding the probability that we get no mice, so none, oops, hold on. That's not proper English. So no mouse till the 5th person. Okay, so if I'm saying my 5th person is a mouse, that means my first 4 are something else, right? So they're failures. So I have, if the probability of success is 0.131, probability of failure is 0.869, and I have 4 failures, right, times my 1 success, 0.131, right? And if you actually go through and calculate that, you get 0.0747. So that's my final answer, okay? Right, and now you can kind of see it worked out here on the left-hand side, okay? Last one is we're saying he would like to interview a student who voted for Wolverine and wants to know the probability that he doesn't find someone until the 4th person. So here we're finding the probability that y is equal to 4, okay? Actually, really, it shouldn't be y because y is like probability for mouse, so I really should use a different variable. If you're talking about a different probability or a different event, you really should use a different variable. So I'll use the variable, I don't know, I'll use the variable w. Sure. So that is, if I'm not getting a success until the 4th person, that means I have 3 failures. So 0.4 to the 3rd power times 0.6. That's my success. Just go through, plug that in a calculator, and figure out what that is. When I did, I got 0.0384. All right, you guys, so that is it for this video on geometric probability and the end of our videos for Unit 5 on probability. Please reach out and let me know if you have questions or want to work through other examples, and I'll see you in the next video in the next unit. Bye, everybody.